Every sunrise reminds us that our very own star is blazing just 93 million miles away, lighting up our world and fueling life on Earth. But how much do you really know about the sun? From its mind-boggling size and fiery surface to the secrets of its core, our closest star is full of wonders you've probably never heard before. Today, we're diving deep into 214 amazing facts about the sun, the star that makes life on our planet possible. The sun is a G-type main sequence star, often classified as a yellow dwarf, with a diameter of roughly 1.39 million kilometers, making it about 109 times wider than Earth. Its immense mass, approximately 1.989 times 1030 kilograms, accounts for about 99.86% of the entire solar system's mass. Located at an average distance of about 149.6 million kilometers from Earth, it takes light about 8 minutes and 20 seconds to travel from the sun to our planet, defining what we call an astronomical unit, AU, a fundamental measurement in astronomy. The sun's composition primarily includes hydrogen, about 74% by mass, and helium, around 24%, with trace amounts of heavier elements such as oxygen, carbon, neon, and iron making up the rest. The sun generates energy through nuclear fusion occurring in its core, where hydrogen atoms fuse under extreme pressure and temperature, roughly 15 million degrees Celsius, to form helium and release massive amounts of energy as photons. This fusion process has powered the sun steadily for approximately 4.6 billion years and is expected to continue for another 5 billion years. Structurally, the sun is composed of several distinctive layers. At its center lies the core, the hottest region where fusion takes place. Moving outward, energy passes through the radiative zone, where photons can take thousands to millions of years to travel due to constant absorption and re-emission. Above this is the convective zone, where energy is transported more rapidly by convection currents, as hot plasma rises and cooler plasma sinks, eventually reaching the sun's visible surface, the photosphere. The photosphere, about 500 kilometers thick, emits the light we see and has temperatures around 55 degrees Celsius. Above the photosphere is the chromosphere, a thin, reddish layer visible during solar eclipses, characterized by temperatures rising from about 4,000 to 25,000 degrees Celsius. Beyond the chromosphere lies the corona, the sun's outer atmosphere, which extends millions of kilometers into space and is paradoxically hotter than the surface, reaching temperatures of 1 to 3 million degrees Celsius. This phenomenon remains an active area of solar physics research. Solar activity on the sun includes a wide variety of dynamic phenomena such as sunspots, solar flares, and prominences. Sunspots are cooler, darker regions on the photosphere resulting from intense magnetic activity that inhibits convection. These spots typically appear in cycles of approximately 11 years, known as the solar cycle, during which the number of sunspots fluctuates from minimum to maximum and back, influencing space weather and conditions on Earth. Solar flares are sudden, intense bursts of radiation caused by magnetic energy releasing from sunspots and other active regions. These flares can emit X-rays and extreme ultraviolet radiation, affecting the Earth's ionosphere and sometimes disrupting radio communications and GPS signals. Coronal mass ejections, often associated with flares, launch massive clouds of charged particles into space, contributing to geomagnetic storms when interacting with Earth's magnetic field. The solar wind is a continuous outflow of charged particles, mainly electrons and protons, that escape the sun's corona at speeds ranging from 300 to over 800 kilometers per second. This plasma forms a vast bubble known as the heliosphere, which envelops the entire solar system and extends well beyond the orbit of Pluto. The solar wind shapes and influences planetary magnetospheres and atmospheres, and it is responsible for phenomena such as the auroras, visible as shimmering lights near the poles of Earth and other magnetized planets. The influence of the sun extends far beyond energy supply. Its magnetic field permeates the solar system, through the interplanetary magnetic field carried by the solar wind. Variations in solar activity impact space weather, which can pose risks to spacecraft electronics, satellites, and even the health of astronauts. Moreover, the solar wind contributes to the gradual erosion of planetary atmospheres, particularly on bodies like Mars, which lack a strong protective magnetic field. Historically, the sun's nature was first scientifically understood in the 19th century, with advances made by astronomers such as Joseph von Fraunhofer, who observed dark absorption lines in the solar spectrum in 1814, now known as Fraunhofer lines, revealing the sun's chemical composition. In the early 20th century, Cecilia Payne-Gaposchkin identified hydrogen as the main component of the sun, shifting previous assumptions about stellar composition. The development of solar telescopes and spacecraft, such as SOHO and the Parker Solar Probe, has allowed increasingly detailed studies of the sun's structure and activity. The sun's energy output, or luminosity, is approximately 3.828 times 1026 watts, which is about 10 billion times the power consumption of humanity on Earth. This energy supports life by driving Earth's climate system and photosynthesis in plants. Changes in solar brightness, although relatively small, can have measurable effects on Earth's atmosphere and climate patterns, highlighting the importance of continuous solar monitoring. On a microscopic level, the sun's core pressure reaches approximately 250 billion atmospheres, conditions necessary for sustaining nuclear fusion. The fusion process follows primarily the proton-proton chain reaction, where hydrogen nuclei combine ultimately to form helium and release energy. This reaction is a balance of forces: gravitational pressure inward and energy-producing fusion outward, maintaining the sun's equilibrium over billions of years. Observations of solar oscillations, known as helioseismology, provide insight into the sun's interior. Waves traveling through the sun cause measurable surface vibrations, which can be analyzed to infer internal temperatures, densities, and flows. This method has allowed scientists to confirm theories about solar structure and dynamics, offering a tool akin to seismology used in earth sciences. In the outer layers, the sun's magnetic field twists and tangles due to differential rotation. Its equator spins faster than its poles, fueling magnetic phenomena such as sunspots and solar flares. This rotation period varies from approximately 25 days at the equator to 35 days at the poles. These changing magnetic fields eventually reconnect, resulting in energetic releases that can influence conditions throughout the solar system. The sun's gravitational force dominates the orbits of all planets, comets, asteroids, and other objects. Its gravitational pull keeps planets moving in elliptical orbits, following Kepler's laws. Despite appearing static in our sky, the sun is moving through the Milky Way galaxy at an average velocity of about 828,000 kilometers per hour, carrying the entire solar system with it. Solar irradiance fluctuates slightly during the solar cycle, varying by about 0.1% between solar minimum and solar maximum. Although small, these changes affect atmospheric chemistry and dynamics, influencing phenomena such as the expansion and contraction of the Earth's upper atmosphere and potentially modulating climate on longer timescales. The solar corona, visible as a glowing halo during total solar eclipses, is a source of high-energy particles and X-rays. Its high temperature is partly explained by magnetic reconnection and wave heating mechanisms, where energy from magnetic fields and waves generated deep within the sun is transferred into the outer atmosphere. This heating creates the solar wind and drives space weather phenomena that extend throughout the solar system. The sun's lifetime spans several phases. Currently in the main sequence phase, the sun converts hydrogen into helium in its core. In about 5 billion years, it will exhaust its core hydrogen, expand into a red giant, and later shed outer layers, leaving behind a dense core as a white dwarf. This stellar evolution shapes the environment for the entire solar system in the long term. The sun's magnetic activity and solar wind also influence comet tails, which always point away from the sun regardless of the comet's direction of travel. As comets approach the sun, solar heating causes sublimation of ices, producing gas and dust tails visible from Earth. These tails provide direct evidence of the sun's influence far beyond the immediate planetary neighborhood. Despite its seemingly constant brightness, the sun produces a vast range of solar storms and space weather events. Understanding these events is vital for protecting modern technological infrastructure and preparing for future space exploration. Solar observation missions continuously provide data to predict solar flares and coronal mass ejections that may impact Earth. Through its complex layers, dynamic magnetic activity, and omnipresent influence, the sun serves as a natural laboratory for understanding stellar physics and the interplay between a star and its planetary system. Studying the sun not only deepens our knowledge of astrophysics, but also enhances our ability to safeguard our technologically dependent civilization from solar-generated hazards. The sun's luminosity has not remained constant throughout its history. It is believed to have increased by approximately 30% since its formation 4.6 billion years ago. This gradual brightening occurs as the fusion of hydrogen into helium slowly alters the composition and pressure balance within the core. Consequently, the evolving energy output has influenced planetary climates over geological time, posing important considerations for Earth's early atmosphere and the development of life. The solar neutrino problem was a significant scientific challenge in the late 20th century, stemming from the observed deficit in the number of neutrinos detected from the sun compared to theoretical predictions. Neutrinos are nearly massless particles produced in vast quantities during nuclear fusion in the core. It was eventually resolved by the discovery that neutrinos oscillate among different types, or flavors, en route to Earth, implying that neutrinos have a small mass and can change identity, which profoundly impacted particle physics and our understanding of the sun's core processes. Sunspots were first systematically recorded by Galileo Galilei and other astronomers during the early 17th century after the invention of the telescope, providing some of the earliest direct evidence of solar activity. These observations revealed that sunspots could appear, change, and disappear over days or weeks, establishing that the sun was not an unchanging, perfect sphere as once believed. Long-term sunspot records have enabled scientists to study solar cycles and correlate solar activity with terrestrial phenomena such as climate variations and geomagnetic storms. The interplay of plasma and magnetic fields on the sun leads to the formation of structures called solar prominences, which are large, bright loops of plasma extending outward from the surface. These prominences are typically anchored to sunspots or active regions, where magnetic field lines protrude into the corona, suspending charged particles. The prominence plasma is relatively cool compared to the surrounding corona, and these features can persist for days to months, occasionally erupting and releasing material into space which may interact with the Earth's magnetosphere. Solar irradiance measurements have been continuously improved by satellite instruments since the late 1970s, allowing for precise monitoring of the energy the sun emits across different wavelengths. By studying variations in solar output, researchers have linked changes to solar cycles and have developed models to forecast their impacts on Earth's atmosphere. This data is crucial for distinguishing natural solar influencers on climate from human-induced effects, refining both climate science and the prediction of space weather. The sun's differential rotation is not just confined to its surface. Heliosismology has revealed that the phenomenon extends through the convective zone, but transitions to nearly uniform rotation in the radiative layer beneath. This boundary, called the tachocline, lies approximately at 0.7 solar radii from the center, and is thought to be the seat of the solar dynamo, the mechanism generating the sun's magnetic field. Understanding the tachocline's dynamics remains a key objective in solar physics, as it relates directly to magnetic cycle variations. At the most fundamental level, the sun's energy generation depends on quantum tunneling, a phenomenon allowing fusion reactions between positively charged protons to occur even at temperatures and pressures lower than classical physics would permit. This process enables hydrogen nuclei to overcome their electrostatic repulsion and initiate the proton-proton chain reaction. Without quantum tunneling, the fusion rates would be vastly reduced, dramatically altering the sun's energy output and its stability. The corona's extreme heat compared to the photosphere has been studied through the observation of sharp temperature gradients and the presence of highly ionized elements such as iron, silicon, and calcium in the solar spectrum. These highly ionized states indicate the presence of temperatures in the millions of degrees Kelvin, far exceeding those of the visible surface. Instruments like the Extreme Ultraviolet Imaging Telescope, EIT, aboard the SOHO spacecraft have mapped this hot plasma, revealing complex magnetic structures that contribute to corona heating. The solar magnetic field lines are continuously reconfigured through a process called magnetic reconnection, where stored magnetic energy is rapidly converted into kinetic energy, heating, and particle acceleration. Reconnection events in the corona are responsible for solar flares, which release energy equivalent to billions of hydrogen bombs in minutes. These flares emit across the electromagnetic spectrum, from radio waves to gamma rays, affecting planetary environments and space-based technologies within minutes to hours of their occurrence. The charged particles streaming from the solar wind interact with Earth's magnetosphere, creating spectacular auroral displays. These interactions energize atmospheric molecules, causing them to emit light in characteristic colors like green and red. Auroras occur primarily near Earth's polar regions, where magnetic field lines converge, allowing solar particles to penetrate deeper into the atmosphere. The study of auroral physics informs scientists about solar-terrestrial coupling and planetary magnetic field structures. Solar spectroscopy, the study of the sun's light spectrum, remains one of the most powerful tools for understanding solar composition and dynamics. By analyzing absorption and emission lines, researchers can identify specific elements and their abundances, as well as measure velocities through Doppler shifts. This technique has revealed differential flows, magnetic field strengths in sunspots, and transient phenomena like spicules, small, jet-like features in the chromosphere that transport energy and mass into the corona. The Parker Solar Probe, launched in 2018, is humanity's closest ever mission to the sun, designed to probe the solar corona and solar wind origins directly. It makes repeated close passes at just 6.2 million kilometers from the sun's surface, enduring extreme heat and radiation to capture in situ measurements. The data from the Parker Solar Probe is revolutionizing our understanding of solar wind acceleration, magnetic field structures, and particle dynamics, providing unprecedented detail about the star that sustains our solar system. Solar prominences and filaments, though closely related, differ in their observational perspective. Prominences are viewed projecting beyond the sun's edge, whereas filaments are seen as dark, sinuous structures against the bright solar disk. Both consist of cool, dense plasma suspended in magnetic loops, and their stability is a subject of ongoing investigation. The mechanisms causing filaments to suddenly erupt and eject plasma into space are important, as these eruptions can trigger space weather effects that reach Earth. Heliosismological observations have also identified large-scale flow patterns inside the sun, such as meridional circulation. This slow movement of plasma from the equator toward the poles and back again plays a role in the transport of magnetic fields within the solar interior. These flows are believed to influence the solar cycle's timing and strength, with deeper and more complex flow patterns becoming detectable through extended observations. The sun's total lifetime on the main sequence phase aligns with its hydrogen fusion period and is determined by its initial mass. Being an average mass star, the sun burns its fuel relatively slowly, enabling it to maintain stable nuclear fusion over billions of years. This long-lived stability is atypical compared to more massive stars, which exhaust their fuel much faster, and less massive stars, which behave differently due to their convective structures. The solar chromosphere, though thin, displays a highly dynamic environment with frequent small-scale eruptions called spicules that can reach heights of up to 10,000 kilometers. These spicules last for only a few minutes, but represent a significant means of energy and mass transfer between the photosphere and corona. High-resolution solar telescopes have allowed scientists to study their properties and frequencies, revealing their potential to contribute to coronal heating. Solar granulation on the sun's surface is a visible manifestation of convection in the convective zone, appearing as a mottled pattern of cells roughly 1,000 kilometers across. These granules are bright centers of hot plasma rising upward, surrounded by cooler plasma sinking along their edges. The constant movement and evolution of granules represent energy transport mechanisms, and studying them helps scientists understand the processes underlying solar surface dynamics. Solar limb darkening is an optical effect caused by looking through cooler and less dense layers at the sun's edge compared to the line of sight when looking directly at the center of the disk. As a result, the sun appears brighter at its center and dims toward its edges or limb. This phenomenon aids astronomers in modeling the temperature and density gradients in the photosphere, providing further constraints on the sun's atmospheric structure. The sun's equator spins faster than its poles because its plasma state does not rotate as a solid body. This differential rotation has profound effects on the magnetic field generation within the sun, contributing to the winding and twisting of magnetic field lines. Observations of this rotation rate difference date back over a century and have been confirmed through modern instruments, making it a fundamental parameter in solar physics. The solar corona's magnetic field structures form large-scale features such as helmet streamers and coronal holes. Helmet streamers are dense loops of plasma that extend outward into the heliosphere, often visible during eclipses as bright arcs. Coronal holes are regions of open magnetic fields that allow high-speed solar wind streams to escape, contributing substantially to space weather effects on Earth, including recurrent geomagnetic storms. The sun's spectral classification as a G/V star denotes both its surface temperature and luminosity class. G/W specifies a photospheric temperature of about 580 Kelvin, while V signifies that it is a main sequence star, burning hydrogen in its core. This classification provides a framework for comparing the sun to other stars and understanding its place in stellar evolution. Magnetic flux tubes on the sun rise from the solar interior and emerge as sunspots or active regions on the photosphere. These flux tubes concentrate magnetic fields, inhibiting convection and creating cooler, darker sunspots. They are responsible for the variety and complexity of solar surface magnetic phenomena, including flares and prominences, and their dynamics are key areas of research using magnetographs and solar imaging. The sun's greenhouse effect, though not in the atmospheric sense as on Earth, can be loosely paralleled by its photospheric and atmospheric layers trapping and re-radiating thermal energy in various spectral bands. The interplay between energy emission, absorption, and scattering within the solar atmosphere affects energy transport and the solar spectrum in subtle ways. Understanding radiative transfer within the sun helps refine models of its energy balance and surface emissions. High-energy particles accelerated by the sun during solar energetic particle (SEP) events pose hazards to space missions and astronauts. These particles originate mainly from flares and coronal mass ejections, traveling at speeds approaching a significant fraction of the speed of light. Space agencies monitor these events closely to provide warnings, underscoring the practical importance of solar physics research for space exploration safety. Solar cycle predictions rely on complex models of magnetic field generation and evolution, incorporating historical sunspot data and heliosismological findings. Although current models can approximate the strength and timing of cycles, uncertainties remain, reflecting the chaotic nature of magnetic processes. Improving prediction accuracy has direct benefits for preparing for periods of intense solar activity and mitigating its impact on technology and infrastructure. The sun's gravitational influence shapes the orbits of all solar system bodies, but it also induces subtle perturbations in orbital motions, detectable with precise measurements. These perturbations played a crucial role in discovering planets like Neptune and dwarf planets by analyzing deviations in orbital paths. Moreover, the sun's gravity well curves spacetime, causing gravitational lensing effects observable in distant starlight passing near its limb. Solar eclipses, produced when the moon passes between Earth and the sun, have historically been vital for scientific discovery. Observations during total eclipses have led to the first measurements of the solar corona and the confirmation of gravitational bending of light as predicted by general relativity. These events continue to offer unique opportunities for studying the sun's atmosphere outside the interference of its intense disk light. The sun generates a complex spectrum containing continuum radiation and numerous spectral lines, resulting from the absorption and emission of photons by atoms and ions in different solar layers. Among these are the Fraunhofer lines, which allowed early astronomers to identify elements present in the sun. Modern spectroscopy has expanded this to include lines from ionized species and molecules, providing a detailed chemical fingerprint of the solar atmosphere. Solar irradiance variability on timescales shorter than the 11-year solar cycle, such as daily or rotational periods, reflects changes caused by features like sunspots and faculae. Faculae are bright regions often surrounding sunspots, increasing the sun's overall brightness even when many dark spots are present. This interplay of light and dark surface features creates complex solar brightness patterns that affect Earth's solar input over short periods. The sun's angular momentum, although a tiny fraction of the total angular momentum of the solar system, results in its rotational flattening, causing a slight equatorial bulge. This deviation from perfect sphericity affects gravitational field measurements and contributes to differential rotation dynamics. The precise measurement of this bulge assists in refining solar interior models and understanding rotational energy distribution. Over the last century, the advent of adaptive optics and space-based solar telescopes has dramatically improved the resolution at which we observe the sun. Ground-based observatories were limited by atmospheric turbulence, but instruments like the Daniel K. Inouye Solar Telescope, DKIST, push resolutions down to tens of kilometers on the sun's surface. These technological advances have unveiled fine-scale structures and rapid temporal variations that deepen our understanding of solar magnetism and plasma physics. In addition to electromagnetic emissions, the sun is a source of gravitational waves, though these are extremely weak and currently undetectable. The sun's internal oscillations and turbulent flows produce minute perturbations in spacetime, yet their amplitude is many orders of magnitude below the sensitivity of current detectors. The study of such phenomena is primarily theoretical, but adds completeness to the spectrum of physical processes occurring in a star. The sun experiences differential rotation not only latitudinally, but also radially. Its outer convective zone rotates more slowly compared to its inner radiative zone. This shear layer, called the tachocline, acts as an interface where strong shear motions can amplify magnetic fields. Magnetic field amplification in the tachocline leads to the cyclic generation and reversal of solar magnetic polarity every 11 years, underlying the magnetic solar cycle observed from Earth. Energy generated in the sun's core is transported outward by photons, but it takes an average of 100,000 years for these photons to reach the surface due to countless absorption and re-emission events. This prolonged journey is known as radiative diffusion. In contrast, convective energy transport through the outer layers is much faster, taking only weeks to days, which helps explain differences in solar surface phenomena and luminosity fluctuations. The sunlit hemisphere of any planet experiences direct solar radiation, but the intensity decreases with the square of the distance from the sun. This inverse square law governs the energy available for planetary climates and influences atmospheric dynamics. Understanding this fundamental relation helps scientists compare solar energy input to planets with varying distances, and thus evaluate their habitability potential. The measurement of solar diameter has historically fluctuated due to observational challenges and atmospheric distortions. Modern measurements utilize space-based instruments and helioseismic models to ascertain the sun's radius with an uncertainty of less than a few kilometers. Tracking tiny changes in the solar radius over the solar cycle can offer insights into the sun's internal dynamics and the effects of magnetic activity on its outer layers. Solar irradiance encompasses a wide range of wavelengths, from infrared through visible light to ultraviolet and X-rays. Each portion of this spectrum affects planetary atmospheres differently. Ultraviolet and X-ray radiation play crucial roles in ionizing upper atmospheres, altering chemical compositions, and driving escape processes. Monitoring the sun's spectrum across these wavelengths is vital for predicting space, weather impacts, and understanding atmospheric evolution. The sun's role as a standard candle in astrophysics relies on well-characterized properties such as luminosity, mass, and spectral class. By comparing other stars to the sun, astronomers can estimate distances and ages of celestial objects. This comparative approach underpins much of stellar astrophysics and contributes to our broader understanding of galactic structures and evolution. Stars like the sun seeds their surroundings with heavier elements through their final evolutionary phases, but during the main sequence, the sun's influence is primarily energy and particle radiation. Nevertheless, solar winds contribute to shaping the solar nebula and planetary atmospheres indirectly by interacting with gas and dust in space. The study of this interaction provides clues to early solar system formation and conditions on nascent planets. The sun's magnetic polarity reverses approximately every 11 years. This flip is part of the solar cycle's magnetic phase lasting about 22 years. During this period, sunspot activity, solar flares, and coronal mass ejections vary in intensity and distribution, linked closely to evolving magnetic field structures. Understanding these polarity reversals assists in anticipating solar activity and its potential effects on Earth and space technologies. Electron density in the sun's corona can vary widely, from about 10·8 electrons per cubic centimeter near the base of the corona to less than 10·6 further out. Measurements from solar eclipses, spacecraft, and radio waves reflected off the corona inform scientists about plasma density profiles. These densities affect how the corona emits radiation and how solar wind accelerates, crucial for modeling heliospheric conditions. The sun's equatorial velocity is roughly 2 kilometers per second, leading to a full rotation every 25 days at the equator, but slower rotations at higher latitudes. This velocity influences the organization and strength of sunspots, which often group in active longitudes correlating with rotational periods. Tracking sunspot movement provides real-time data about solar rotation and its temporal variations. Solar irradiance models must include the effects of solar faculae, which are bright features that increase solar output despite the presence of dark sunspots. Faculae contribute more irradiance during the solar cycle maximum, partially compensating for sunspot dimming. This balance ensures the sun's brightness remains relatively stable over the cycle, underscoring the complexity of solar surface brightness variations. Solar flares and coronal mass ejections originate from the rapid reconfiguration of twisted magnetic field lines in active regions. These powerful eruptions release electromagnetic radiation and vast clouds of charged particles, which can accelerate to millions of kilometers per hour. When aimed toward Earth, such eruptions can induce energetic particle storms that disrupt satellite operations, power grids, and radio communications. The discovery of the solar neutrino flux deficit led to revisiting solar models and neutrino physics, fostering collaboration between astrophysicists and particle physicists. Experiments like the Sudbury Neutrino Observatory, SNO, demonstrated neutrino oscillations, confirming both a solar model and advancing fundamental physics. This intersection illustrates the sun's role as a natural laboratory beyond classical astronomy. Despite its brightness, the sun's emitted light is not uniform across its disk due to limb darkening and the irregular distribution of surface features. High-resolution mapping of these brightness variations informs about convective processes, magnetic activity, and energy transport. Such mappings improve solar irradiance reconstructions essential for climate models and space weather predictions. Solar wind particles carry with them the sun's magnetic field, known as the Interplanetary Magnetic Field (IMF). The IMF is embedded in the solar wind and spirals outward due to the sun's rotation, forming the Parker spiral. This structured magnetic field modulates cosmic ray penetration, planetary magnetospheres, and influences charged particle propagation through the heliosphere. The sun's spectrum includes absorption lines known as Fraunhofer lines, caused by gases in the solar atmosphere absorbing specific wavelengths. These lines have enabled remote sensing of the sun's elements and the physical conditions in its atmosphere since the 19th century. Detailed analysis of these lines continues to provide insights into temperature, pressure, composition, and motions in different solar layers. Solar irradiance fluctuations affect Earth's climate system differently depending on timescales. Long-term variations correlate with ice age cycles, while shorter cycles influence weather patterns. Numerical climate models incorporate solar variability to attribute observed climate changes correctly. Ongoing research seeks to quantify the extent of solar influence relative to anthropogenic factors. Finally, the sun serves as a primary benchmark for studying other stars, providing a detailed standard against which stellar properties are measured and interpreted. Its proximity allows for observations at resolutions not possible with other stars, offering unparalleled insights into stellar phenomena. Studying the sun thus enhances our understanding of stellar evolution, magnetic activity, and planetary system interactions across the universe. The sun's mass loss through the solar wind and radiation is a subtle but ongoing process that slowly reduces its total mass over time. Current estimates suggest the sun loses about 4 million tons of mass every second, primarily via the solar wind, a continuous stream of charged particles, and electromagnetic radiation. Although this rate seems enormous, it is negligible compared to the total solar mass, resulting in a mass loss of roughly 1/10,000% over the sun's entire lifetime on the main sequence. The sun's gravitational influence establishes the so-called Hill sphere, a region extending about 1 to 2 light-years around it, where its gravity dominates over that of neighboring stars. This gravitational boundary confines the majority of the solar system's objects, including the distant Oort cloud, a hypothetical spherical shell of icy bodies thought to be the source of long-period comets. The vast extent of the Hill sphere underscores the sun's role as the central anchor of a far-reaching cosmic environment. Solar magnetic flux emergence frequently occurs in the form of ephemeral regions, small magnetic bipoles that appear and decay across the photosphere on timescales of hours to days. These ephemeral regions contribute substantially to the flux budget of the sun's magnetic field, especially during solar minimum phases. Their constant formation and cancellation help maintain a dynamic magnetic carpet that influences coronal heating and the basal level of solar activity. The sun's photosphere exhibits supergranulation patterns, convective cells much larger than the granules, typically around 30,000 kilometers in diameter. These cells channel magnetic fields into networks at their boundaries, organizing the solar magnetic landscape on larger scales. The characterization of supergranulation reveals important links between convection, magnetism, and solar atmospheric dynamics. The concept of solar twins, stars nearly identical to the Sun in mass, temperature, and composition, has been critical in comparative stellar studies. Identifying and studying these solar analogs helps astronomers understand the Sun's place in stellar evolution and gauge the potential for habitable planets around similar stars. Precise spectroscopic surveys have found only a handful of such solar twins within a few hundred light-years, testifying to the unique combination of conditions the Sun possesses. Solar differential rotation induces the twisting of magnetic field lines, which in turn fosters a cycle of magnetic field lines stretching and reconnection, known as the solar dynamo process. This dynamo operates most efficiently in the tachocline, the thin shear layer between the radiative and convective zones, and is responsible for the periodic reversal of the Sun's global magnetic field polarity. This cyclical dynamo action underpins the roughly 11-year sunspot and magnetic cycle observed from Earth. The Sun emits neutrinos through several nuclear fusion pathways, including the dominant proton-proton chain, as well as the carbon-nitrogen-oxygen (CNO) cycle, which contributes a smaller fraction of the total energy production. Recent experimental progress in neutrino detection has confirmed the CNO cycle's existence in the Sun, providing direct insight into stellar fusion processes and element cycles in stars with masses similar to or greater than the Sun. Solar irradiance varies not only in total output but also in spectral distribution, with ultraviolet UV and extreme ultraviolet EUV wavelengths showing the largest relative changes during the solar cycle. These shorter wavelengths influence Earth's upper atmosphere more directly by ionizing and heating the thermosphere and ionosphere, affecting satellite drag and radio signal propagation. Monitoring these spectral changes is essential for understanding and predicting impacts on space weather and communication systems. The excitation of acoustic oscillations in the Sun arises from turbulent convection in the outer layers, giving rise to pressure waves that resonate within the solar interior. These waves surface as small periodic changes in brightness and velocity, allowing heliosseismologists to create three-dimensional models of the Sun's internal structure. Detailed heliosseismic data have enabled the refinement of solar models, providing tight constraints on sound speed profiles, rotation rates at different depths, and even the presence of asymmetries. Magnetic flux ropes formed in the solar corona are twisted bundles of magnetic fields that can store vast amounts of energy, sometimes erupting violently as coronal mass ejections, CMEs. The sudden instability and eruption of these flux ropes inject energetic particles and magnetic fields into the solar wind, significantly disturbing interplanetary space. Understanding the formation, evolution, and eruption triggers of flux ropes is crucial for forecasting extreme space weather. The Sun supports a variety of wave phenomena in its atmosphere, including Ulfvén waves, magnetohydrodynamic waves propagating along magnetic field lines. These waves transport energy from the turbulent convection zone upward into the corona and solar wind. Although their exact contribution to coronal heating remains under investigation, Ulfvén waves are recognized as key components in transferring momentum and energy within the solar atmosphere. Solar observations during the Maunder minimum, roughly 1645–1715, revealed a prolonged period of exceptionally low sunspot numbers, correlating with the Little Ice Age on Earth. This historical episode demonstrated the potential link between extended periods of reduced solar activity and global climate effects, although it remains a subject of active research to quantify the connections precisely. The Maunder minimum serves as a natural experiment for understanding the impact of solar variability beyond typical solar cycles. Spicules, the thin, jet-like features evident in the chromosphere, have been categorized into two types: Type I, which have longer lifetimes and slower speeds, and Type II, shorter-lived and faster. Recent high-resolution imaging has uncovered their rapid dynamics and possible role in channeling mass and energy into the corona via plasma heating. Studying spicule formation mechanisms advances the understanding of chromospheric and coronal coupling. The Sun produces a solar acoustic cutoff frequency, above which acoustic waves produced in the convection zone cannot propagate into the atmosphere and are instead reflected back toward the interior. This cutoff frequency, approximately 5.3 MHz, helps define the acoustic cavity confines and influences the observed oscillation modes. Detection and analysis of wave power at frequencies near this cutoff yield insights into energy transport processes and atmospheric vertical stratification. Solar bright points are small, intense magnetic features that brighten in the photosphere and lower chromosphere, often observed in regions surrounding sunspots or faculae. These bright points correspond to concentrations of kilogauss magnetic fields, and their dynamics reflect the interactions between magnetic fields and convective motions. Understanding them helps reveal how magnetic energy cascades into the solar surface layers and contributes to heating. The magnetic carpet of the Sun, composed of pervasive ephemeral magnetic elements, has a lifetime roughly equivalent to the solar rotation period of about 27 days. This continual renewal influences the basal, or quiet, Sun's magnetic activity, and is thought to provide a source of stress and magnetic reconnection events in the corona, even during sunspot minima. It exemplifies the magnetically restless nature of the solar surface. The Sun's radiative zone, extending from the core to about 0.7 solar radii, is highly transparent to photons but extremely dense, resulting in an intense diffusion process where photons are absorbed and re-emitted thousands of times before escaping. In this zone, thermal energy transfer occurs primarily through radiative diffusion rather than convection, contributing to the Sun's stable energy outflow. The radiative zone's uniform rotation contrasts with the differential rotation seen in the outer convective zone. Solar magnetic fields can become twisted and sheared by convective motions, storing energy in complex configurations called sigmoids, which often precede solar eruptions. These sigmoidal structures, visible in ultraviolet and X-ray images of the corona, are indicators of magnetic instability and potential flare or mass ejection sites. Systematic studies of sigmoids provide predictive insight into solar storm precursors. The temperature minimum region sits between the photosphere and chromosphere at about 500 kilometers above the Sun's visible surface and has a temperature near 44.0 K, lower than both layers around it. This minimum acts as a transitional thermal boundary, impacting radiative fluxes and the formation of certain molecules and spectral lines. Understanding this region clarifies the temperature gradient's complexity in the solar atmosphere. Solar filaments, when viewed against the bright solar disk, appear as dark, elongated structures, dense, cool plasma suspended by magnetic fields. In contrast, these same structures are called prominences when observed projecting beyond the solar limb. Filaments often align with regions of magnetic polarity inversion, where the magnetic field changes direction over short distances, emphasizing their magnetic origin. Observations have confirmed that the Sun's photosphere contains various elements in ionization states determined by its temperature and density. For example, neutral hydrogen dominates the cooler lower photosphere, whereas ionized calcium and iron lines emerge from hotter, higher layers. These spectral details enable precise diagnostics of vertical temperature profiles and chemical abundances. The Sun's overall magnetic field strength, averaged over the entire photosphere, is relatively weak, about 1 Gauss, slightly stronger than Earth's magnetic field at the surface. However, concentrated magnetic flux regions within sunspots can reach intensities exceeding 3,000 Gauss, thousands of times stronger. Such dramatic contrasts demonstrate the highly heterogeneous magnetic nature of the solar surface. The solar transition region, a thin and complex boundary lying between the chromosphere and corona, experiences a rapid increase in temperature over a few hundred kilometers. going from tens of thousands to over 1,000,000 Kelvin. This steep temperature gradient plays a vital role in plasma ionization and the onset of the solar wind. Observations of emission lines from highly ionized species in this region provide clues about energy transport mechanisms at work. Solar faculae, bright, small-scale structures associated with magnetic fields, tend to cluster near sunspots but appear all over the photosphere during solar maximum. Unlike dark sunspots, faculae enhance the sun's brightness, and collectively, they contribute significantly to irradiance variations. Their influence helps explain why the sun becomes overall brighter during periods of intense magnetic activity. Macroscopic solar eruptions often generate shock waves in the solar atmosphere and heliosphere, including coronal shock waves and interplanetary shocks. These disturbances can accelerate particles to relativistic speeds, creating solar energetic particle events detected throughout the solar system. Such solar-driven shocks affect space weather conditions, having implications for planetary protection and satellite operations. Solar differential rotation also manifests in subsurface layers as revealed by heliosysmic inversions, showing complex shear layers beneath the tachocline. These layers potentially influence the formation and buoyant rise of magnetic flux tubes that eventually surface as sunspots. The detailed structure of these shear zones is pivotal to calibrating dynamo models and the timing of solar cycles. The sun's limb darkening profile is wavelength dependent. Shorter wavelengths like blue light exhibit stronger limb darkening than longer wavelengths such as infrared. This dependency is connected to the depth of photon formation at various wavelengths and the temperature gradient of the photosphere. Accurate limb darkening measurements across spectra assist in refining solar atmosphere models and in calibrating stellar photometry for distant stars. Solar UV radiation, particularly within the Lyman alpha line at 121.6 nanometers, contains a significant portion of the sun's high-energy output and drives photochemical processes in planetary atmospheres. Variability in this UV emission during the solar cycle influences ionospheric densities and the rates of atmospheric escape on planets such as Mars and Venus. Space missions routinely monitor UV spectral irradiance to characterize solar-terrestrial interactions. Solar neutrinos escape the sun's core nearly unimpeded, providing a direct probe into ongoing fusion reactions. Their detection requires massive, deep underground detectors shielded from cosmic rays. The flux measured aligns closely with theoretical predictions once neutrino oscillations are taken into account, validating standard solar models with remarkable precision. The sun's magnetic flux emergence rate varies over the solar cycle, reaching its maximum during solar maximum, when new active regions form more frequently. Observations show that the sun injects more magnetic energy into its atmosphere during these active phases, corresponding to increased flare, prominence, and CME occurrences. Tracking magnetic flux emergence thus serves as an important proxy for predicting solar activity levels. Heliosysmology has detected solar torsional oscillations, bands of faster and slower rotation migrating over the solar surface and interior in concert with the solar cycle. These oscillations are believed to be linked to the magnetic dynamo, evidencing feedback between magnetic fields and plasma flows. Their study enhances understanding of the solar cycle's physical drivers and temporal evolution. The sun's photospheric temperature reflects a balance between energy production in the core and energy loss via radiation at the surface. This equilibrium maintains the star's relatively stable brightness and size, as dictated by the virial theorem, which connects the balance between kinetic and potential energies in a gravitationally bound system. Disruptions to this equilibrium, such as during evolutionary phases, cause significant changes in solar output and structure. Chromospheric plages are bright regions seen in certain spectral lines, such as the calcium H and K lines, and are associated with concentrations of magnetic fields in the chromosphere. These plages often correspond spatially with faculae and active regions, serving as indicators of enhanced chromospheric heating. Monitoring plages is particularly useful for reconstructing past solar activity from historic spectroscopic observations. The solar photosphere is permeated by relatively cool regions called intergranular lanes, which lie between granules where plasma sinks back into the convection zone. These lanes are also sites of enhanced magnetic field concentration, acting as channels for magnetic flux accumulation. Their spatial and temporal interactions with granules contribute to the complex magnetic pattern observed at the solar surface. During total solar eclipses, observations reveal that the solar corona contains large-scale structures, such as coronal loops and streamers shaped by magnetic fields. These structures delineate regions of closed and open magnetic topology, influencing where the solar wind originates. Coronal imagery during eclipses has been instrumental in understanding the corona's magnetic nature and its relationship to solar wind sources. Coronal holes are persistently observed as dark, low-density regions in ultraviolet and X-ray wavelengths, corresponding to areas of open magnetic fields. These holes are prolific sources of fast solar wind streams that modulate the Earth's geomagnetic environment for extended periods. Their size and location change with the solar cycle, often appearing near the poles during solar minimum and at lower latitudes near solar maximum. Magnetic field polarity reversals during the solar cycle are accompanied by changes in heliospheric current sheet structure, a vast surface extending throughout the heliosphere where the magnetic polarity flips. The warped form of the current sheet plays a role in modulating cosmic ray propagation throughout the solar system. Understanding this structure supports our grasp of cosmic ray flux variations and their impacts on Earth. Sunspot umbra, the dark central region of sunspots, have temperatures typically around 35°C to 45°C Kelvin, significantly cooler than the surrounding photosphere. This temperature deficit stems from inhibited convective heat transport by strong magnetic fields reaching several kilogauss in strength. The size, structure, and development of sunspot umbra provide insight into magnetic field stability and solar activity timescales. Solar flares are classified by their X-ray brightness in the 1 to 8 angstrom range, with classes ranging from A, B, C, M to the most intense X-class flares. X-class flares can release energy up to 1032 ergs, equivalent to billions of hydrogen bombs detonating simultaneously. These energetic events produce a spectrum of radiation and charged particles that pose significant space weather hazards. The solar corona emits strongly in soft X-rays, which are absorbed by Earth's atmosphere and must be observed from space-based platforms. These emissions are sensitive indicators of coronal temperature and magnetic activity, allowing real-time monitoring of solar conditions relevant to space weather forecasting. Instruments like the X-ray telescope on the Hinot satellite have provided unprecedented observations of this high-energy solar emission. Solar active regions, distinguished by strong magnetic fields and enhanced emissions across the spectrum, tend to cluster in active longitudes, where the probability of flare occurrence is elevated. These preferred zones suggest underlying magnetic structures or patterns in the solar interior that concentrate activity longitudinally. Understanding active longitudes aids in anticipating flare distributions and timing. Spectropolarimetry, measuring the polarization of light from the sun, is a powerful technique for mapping magnetic field strengths and orientations in solar structures. By analyzing Zeeman splitting in spectral lines, scientists reconstruct three-dimensional magnetic configurations critical for studying sunspots, prominences, and flares. These measurements are key to unraveling the magnetic complexity of the solar atmosphere. Solar irradiance, integrated over all wavelengths, defines the total solar energy input to Earth and other planets. Variability in this input modulates climate forcing and atmospheric chemistry, influencing surface conditions and habitability. Long-term solar irradiance reconstructions based on proxies like tree rings and ice cores complement modern satellite data, extending our knowledge of solar influence into the pre-instrumental past. The Parker spiral shape of the interplanetary magnetic field results from the solar wind carrying the sun's magnetic field outward while the sun rotates. This spiral geometry influences the propagation paths of energetic particles and the structure of the heliosphere. Understanding the Parker spiral is fundamental for modeling space weather and cosmic ray trajectories in the solar system. Solar gravitational redshift causes photons to lose a small amount of energy as they escape the sun's gravitational potential well, leading to a measurable shift toward longer wavelengths. This effect, consistent with predictions from general relativity, amounts to roughly 2 parts per million in frequency shift for visible light. Measuring gravitational redshift in solar spectral lines provides a direct test of Einstein's theory under stellar conditions. The sun's differential rotation leads to the migration of surface features, such as sunspots toward the equator as the solar cycle progresses, a pattern known as Spur's law. This equatorward drift is evident in butterfly diagrams mapping sunspot latitude over time, reflecting underlying changes in magnetic field generation and distribution. Spur's law remains a fundamental observational constraint on solar dynamo models. Transition region explosive events are brief, intense bursts of heating and plasma acceleration detected in ultraviolet spectra, believed to result from magnetic reconnection. These micro-flare-scale events may contribute some heating to the upper atmosphere and supply seed populations for larger eruptions. Continuous observations by solar missions like IRIS have expanded knowledge of these dynamic processes on small scales. The sun's center of mass, or barycenter, is not fixed but moves due to the gravitational influences of orbiting planets, particularly Jupiter and Saturn. This movement affects the solar inertial motion and has been scrutinized for potential correlations with solar activity cycles, though causative links remain unconfirmed. Monitoring barycentric motion adds nuance to models of the sun's rotational and magnetic behavior. Solar ultraviolet and X-ray emissions create and maintain Earth's ionosphere, which is crucial for radio communication and satellite navigation. Variations in these emissions, driven by solar activity, influence ionospheric density and structure. Space weather forecasting relies heavily on real-time solar observations to predict ionospheric responses vital to modern technology. Heliosismology also reveals the presence of torsional oscillations propagating through the sun's convection zone, subtle shifts in zonal flows that correlate with the solar activity cycle. These oscillations reflect the interplay between magnetic forces and plasma dynamics inside the sun. Studying their speed and propagation sheds light on internal solar dynamo mechanisms. The abundance of lithium in the sun's photosphere is markedly lower than in most meteorites, indicating that lithium has been depleted in the outer solar layers over billions of years through nuclear reactions and mixing processes. This depletion serves as a proxy for modeling stellar interior mixing and evolution in solar-type stars. Lithium observations inform the understanding of stellar life cycles and chemical processes. The sun's photosphere exhibits intricate structures known as bright points and faculae, which are more evident near the solar limb due to enhanced contrast. These features result from localized magnetic concentrations altering the opacity and temperature gradient in the photosphere. Their presence influences the net solar brightness and variability. Solar tornadoes are rotating magnetic structures observed in the solar atmosphere, exhibiting swirling plasma flows aligned with twisted magnetic fields. These events can reach thousands of kilometers tall and last from minutes to hours, and they may play a role in transporting energy and mass into the corona. Investigating solar tornadoes expands the understanding of plasma dynamics and magnetic topology. Observations of the solar irradiance spectrum reveal the presence of continuous and line emissions spanning from radio waves to gamma rays. illustrating the sun's broad electromagnetic output. Each spectral band originates from different physical processes and layers, making multi-wavelength observations essential for comprehensive understanding. Instruments designed to capture this range help decode the sun's atmospheric layers and activity states. The solar radius, conventionally taken as 695,700 km, subtly varies with solar activity, showing variations on the order of a few tens of kilometers over the solar cycle. These radius changes are linked to thermal and magnetic pressure variations in the sun's outer layers. Measuring and understanding solar radius variability contributes to insights on solar atmospheric expansion and contraction. The photospheric magnetic field is organized into network and internetwork regions, with network fields concentrated at supergranular cell boundaries and internetwork fields distributed more sparsely throughout the cells. The interactions and evolution of these fields influence chromospheric heating and contribute to the complex magnetic environment sustained over the solar surface. Studying these features illuminates the fundamental processes driving solar magnetism. Solar radiative transfer involves carefully balanced absorption, emission, and scattering processes, particularly in the photosphere and lower atmosphere. Line formation occurs under non-local thermodynamic equilibrium, non-LTE conditions, complicating spectral analysis. Accurately modeling radiative transfer is key to extracting physical parameters such as temperature, density, and composition from solar spectra. Solar flares sometimes produce white light emission, a sudden increase in visible continuum radiation, indicating intense energy deposition deep in the photosphere or lower chromosphere. These white light flares represent some of the most energetic phenomena on the sun, reflecting rapid plasma heating and particle acceleration. Their study links flare energetics across wavelengths and informs flare prediction models. The solar corona shows quasi-periodic pulsations during flares, manifested as periodic variations in emission in X-ray and radio wavelengths. These pulsations are thought to arise from magneto-hydrodynamic oscillations and wave-particle interactions in flare loops. Analysis of these oscillations contributes to understanding flare energy release and particle acceleration. Solar X-rays emitted during flare events ionize the Earth's upper atmosphere instantaneously, affecting the D-layer of the ionosphere within minutes. This ionospheric disturbance causes shortwave radio blackouts, mostly impacting high-frequency communication and navigation systems. Monitoring solar X-ray flux supports issuing timely alerts for such disruptive solar events. Solar differential rotation patterns vary over the solar cycle, with the equator spinning slightly faster during solar maximum and slowing during minimum. These subtle rotational changes are measured via sunspot tracking and Doppler velocity measurements. They reflect dynamic feedback between magnetic fields and convective flows in the solar interior. The sun's core density is approximately 150 grams per cubic centimeter, roughly 3 times the density of lead, due to immense gravitational compression. Such high densities facilitate the conditions required for proton-proton fusion reactions. Precise knowledge of core density aids in modeling stellar structure and understanding the fundamental physics of energy generation. Solar radio emissions arise from various mechanisms including thermal bremsstrahlung, gyrosynchrotron radiation, and plasma emission, generated by electron beams in active regions. Different radio bursts have distinctive temporal and spectral signatures, used to diagnose solar flare and coronal mass ejection properties. Radio astronomy offers a complementary window into solar activity and plasma conditions. The sun's magnetic field plays a role in suppressing turbulent convection beneath sunspots, creating the observed temperature deficit responsible for their dark appearance. This magneto-hydrodynamic interaction is studied extensively through magnetoconvection simulations. Understanding sunspot formation enhances knowledge of magnetic flux dynamics and energy transport. Long-term solar spectral observations show subtle but systematic variations in solar line depths and profiles, reflecting changes in temperature, turbulence, and magnetic fields. These spectral diagnostics enable reconstructions of historical solar activity and contribute to heliophysics databases. They also provide calibration standards for stellar spectroscopic studies. Solar differential rotations, radial gradient changes near the lower convection zone boundary, called the tachocline, which acts as a shear layer crucial for magnetic field amplification. This thin region, just a few percent of the solar radius and thickness, is believed to store and organize toroidal magnetic fields prior to their emergence at the surface. The tachocline is thus a central focus for understanding the solar dynamo's origin. The Sun contributes to the cosmic gamma-ray background by producing gamma rays through nuclear interactions during solar flares. Although these energetic photons are rare compared to other solar emissions, their detection provides unique insights into high-energy particle acceleration and nuclear processes. Spaceborne gamma-ray spectroscopy enables these observations. The steady outflow of solar wind generates a comet-like tail of plasma extending in the opposite direction of the Sun's motion through the interstellar medium. This heliodyle is shaped by the interaction between solar wind and inflowing interstellar gas, with complex structures revealed by spacecraft data. Studying the heliodyle informs about the boundary conditions of the heliosphere and the Sun's journey through the galaxy. The Sun's motion around the barycenter of the solar system, influenced predominantly by Jupiter, introduces subtle variations in Earth's orbital period, known as Milankovitch cycles. These cycles affect Earth's climate over long timescales and are compounded by solar luminosity changes. Understanding these gravitational interactions forms a holistic view of Earth's climate drivers. Enhanced solar ultraviolet flux during solar maximum leads to increased ionospheric densities, which in turn cause enhanced drag on low Earth orbit satellites. Operators account for this dynamic environment to adjust satellite trajectories and mission planning. Continuous solar monitoring supports the mitigation of space debris and collision risks. Solar spicules can transfer substantial mass from the chromosphere into the corona, with total mass flux exceeding that of the solar wind. This mass supply helps sustain the corona's plasma environment and may play a role in solar wind acceleration. Investigating spicules bridges the understanding between lower solar atmosphere dynamics and heliospheric plasma. The Sun's photospheric pressure averages about 1 × 10⁵ pascals, about 1 atmosphere, at the visible surface, decreasing exponentially with height. Measuring pressure gradients informs the modeling of atmospheric layers and energy transport. Variations in pressure affect spectral line broadening, which aids in diagnostic studies of atmospheric conditions. Overall, the Sun serves as a benchmark for stellar astrophysics, illustrating principles governing star formation, evolution, and magnetic activity. Its close proximity allows detailed physical measurements, providing a valuable laboratory that complements and calibrates observations of stars throughout the galaxy. Continued study of the Sun advances our understanding of stars' roles in cosmic evolution and planetary system development. Solar active longitudes, regions on the Sun's surface where magnetic activity preferentially occurs, have been observed to persist for several solar rotations, sometimes lasting months or even years. These longitudinal zones of concentrated sunspot emergence and flare occurrence illustrate that solar magnetic flux is not distributed randomly, but instead appears organized by subsurface processes. Studying these persistent active longitudes helps reveal the spatial patterning of the solar dynamo and magnetic field generation inside the Sun. The rate at which the Sun expels its magnetic fields into interplanetary space varies significantly throughout the solar cycle. During solar maximum, more frequent and intense events such as coronal mass ejections contribute to injection of magnetic flux into the heliosphere. This episodic release of magnetic energy, not only alters conditions in the near-Earth environment, but also modulates the overall strength and structure of the interplanetary magnetic field. Solar ultraviolet (UV) emission lines originating from ionized helium, He II at 30.4 nm, serve as important diagnostics of the transition region between the chromosphere and the corona. The intensity and profile of these lines fluctuate with solar activity, providing insight into temperature gradients and heating processes occurring in this complex boundary region. Instruments on spacecraft, such as the Solar Dynamics Observatory, have enabled continuous monitoring of He II emissions, improving our knowledge of solar atmospheric dynamics. In addition to the familiar proton-proton chain, the Sun also produces a small but significant flux of neutrinos from the carbon-nitrogen-oxygen (CNO) fusion cycle. Although the CNO cycle contributes only about 1–2% of the Sun's total energy output, its presence confirms that catalytic reactions involving heavier elements operate in stellar cores. Recent neutrino detections from CNO processes have helped verify theoretical models of stellar fusion pathways applicable to more massive stars. The Sun's magnetic field periodically produces intense, small-scale structures known as magnetic bright points. These features, often less than 200 kilometers across, are associated with kilogauss strength fields that stand out against the photospheric background. Magnetic bright points are critical contributors to the basal heating of the solar atmosphere and to the complex interplay of magnetic fields and plasma flows in the near-surface layers. Solar flare ribbons, bright elongated regions observed in chromospheric wavelengths such as hydrogen alpha, mark the footprints of magnetic loops involved in flare energy release. Their motion away from sunspot regions during flare progression maps the process of magnetic reconnection occurring in the corona. By studying the dynamics of flare ribbons, researchers gain valuable constraints on the timing and geometry of magnetic energy conversion. The coronal heating problem, explaining why the solar corona is significantly hotter than the underlying photosphere, has prompted investigations into various candidate mechanisms such as nanoflares, Ulfane wave dissipation, and resistive magnetic reconnection. While no single process fully accounts for the observed coronal temperature and heating uniformity, a combination of small-scale magnetic activity and wave propagation are widely considered central contributors. Ongoing observations and simulations aim to quantify the relative contributions of these mechanisms. Sunspot penumbrae, the lighter, filamentary regions surrounding the darker umbra, exhibit complex magnetic and flow patterns with inclined magnetic fields and fast plasma motions known as the Evershed flow. These horizontal outflows along penumbral filaments represent convective processes modified by strongly inclined magnetic fields. Investigations of penumbral structures deepen understanding of magnetoconvection and the intricate coupling between magnetic fields and fluid dynamics on the Sun. The solar wind experiences a remarkable acceleration from near-zero speed in the low corona to hundreds of kilometers per second by the time it reaches Earth's orbit. This acceleration is driven primarily in the corona by pressure gradients associated with high electron temperatures and magnetic forces. Coronagraph and in situ spacecraft measurements show that this acceleration region extends several solar radii from the Sun's surface, emphasizing the dynamic coupling between the corona and interplanetary space. Solar prominences display two general morphologies: quiescent prominences, which slowly evolve and can persist for weeks, and active prominences, associated with flare-productive regions and prone to eruption. Quiescent prominences often form in high-latitude regions and contain dense, cool plasma embedded in magnetic fields that are nearly horizontal to the solar surface. Understanding the magnetic support and destabilization of different prominence types informs models of mass loading and mass release processes in the solar atmosphere. At the boundary of the solar corona lies the source surface, typically defined around 2.5 solar radii, where magnetic field lines open into space and the solar wind is fully accelerated. This concept simplifies complex coronal magnetic topologies into open and closed field regions, and is used extensively in modeling the heliospheric magnetic field. The source surface location and shape vary with solar activity, affecting solar wind routes and magnetic connectivity with planetary environments. The sun's granulation pattern, caused by convection in the outermost layers, shows characteristic lifetimes on the order of 5 to 10 minutes. Each granule, approximately 1,000 kilometers across, represents the top of a convection cell, where hot plasma rises before cooling and descending along intergranular lanes. High-resolution imaging reveals a continuous turnover of granules, which plays a fundamental role in transporting energy outward and generating small-scale magnetic fields. The intensity of solar X-ray emissions varies dramatically with solar flares, increasing by factors of up to 10,000 or more in short periods. These rapid enhancements originate in flare loops and active regions where hot plasma, tens of millions of Kelvin, is confined by strong magnetic fields. X-ray monitoring is critical for early detection of solar flares and predicting their potential technological impacts on satellites and communication systems. Observations show that the sun's equatorial diameter is marginally larger, by about 10 kilometers, than the polar diameter due to rotational flattening. Although this oblateness is minuscule relative to the sun's total size, it affects solar gravity and angular momentum calculations. Precision measurements with space-based solar observatories help to characterize this shape, contributing to improved models of solar rotation and internal structure. The solar atmosphere hosts a variety of wave modes, including magnetocaustic waves and Ulfane waves, each propagating along or across magnetic field lines with distinct characteristics. These waves transport energy away from turbulent convective zones, potentially fueling coronal heating and the acceleration of the solar wind. Observational evidence from spectroscopy and imaging supports their presence, but quantifying their energy contributions remains an active area of research. The elemental abundance of heavy metals, such as iron, in the solar photosphere is used as a standard reference for metallicity in other stars. Solar metallicity values inform models of stellar formation and evolution, influencing opacities and nuclear reaction rates. Spectroscopic measurements confirm that iron constitutes about 0.14% of the sun's mass, playing a pivotal role in defining the sun's radiative properties. Solar limb darkening follows a predictable pattern, where intensity decreases closer to the solar limb due to the optical depth and temperature gradient in the photosphere. This effect varies with wavelength, being more pronounced at shorter wavelengths such as ultraviolet light. Limb darkening measurements assist with calibrating solar observations and improving models of stellar atmospheres in general. The kinetic temperature of electrons in the solar corona exceeds that of ions, a condition explained in part by anisotropic heating processes and wave-particle interactions. This electron-ion temperature disparity influences the ionization states and emission line ratios observed in the corona, serving as diagnostics of plasma heating and acceleration mechanisms. Measurements from ultraviolet and X-ray spectroscopy aboard spacecraft have confirmed this non-equilibrium state. Solar filaments often form over magnetic polarity inversion lines, boundaries on the sun's surface where the direction of the magnetic field reverses. These regions collect dense plasma suspended by magnetic tension, appearing as dark ribbons in H-alpha imaging against the bright solar disk. The stability of filaments is closely tied to the underlying magnetic configuration, and their eventual eruption frequently precedes coronal mass ejections. The magnetic flux emergence rate on the sun varies not only over the solar cycle, but also on shorter timescales, with ephemeral regions forming and decaying within days. These regions represent small-scale bipoles that contribute to the continuous recycling of magnetic fields on the solar surface. Their cumulative effect sustains a dynamic and magnetically complex photosphere, even during solar minimum periods. Solar ultraviolet emissions directly drive ionization reactions in outer planetary atmospheres, shaping atmospheric chemistry and escape rates. For example, increased UV flux during solar maximum enhances the production of ions in Earth's ionosphere and can increase the rate of hydrogen escape from Mars' thin atmosphere. These processes demonstrate the Sun's role as a key agent of planetary atmospheric evolution. The propagation of solar energetic particles, SEPs, through the heliosphere is influenced by the structure of the interplanetary magnetic field, especially the Parker spiral shape shaped by solar rotation and the outward solar wind. SEPs can be rapidly transported along field lines, reaching planets ahead of coronal mass ejections themselves. Modeling SEP trajectories is essential for space weather forecasting and astronaut safety. Solar tornadoes are large-scale rotating plasma structures observed in extreme ultraviolet wavelengths, sometimes extending thousands of kilometers in height. These rotating features are associated with twisted magnetic fields and can display complex motions, including oscillations and vortex flows. Solar tornadoes have been proposed as conduits for energy and mass transport from the chromosphere into the corona, contributing to coronal dynamics. Heliosysmic inversions have revealed that the Sun's rotation rate exhibits bands of alternating faster and slower zonal flow migrating equatorward and poleward over the solar cycle. These so-called torsional oscillations correlate with magnetic activity cycles and provide clues to the underlying dynamo processes driving the solar cycle. Monitoring these flow patterns helps constrain solar interior dynamics and predict solar activity variations. The Sun's total output of neutrinos is approximately 2 × 10^38 particles per second, reflecting the enormous rate of nuclear fusion at its core. As neutrinos interact only weakly with matter, most escape directly into space, providing a nearly instantaneous glimpse into the core conditions. Ground-based neutrino detectors use rare interaction events to measure this flux, which matches theoretical models after accounting for neutrino oscillations. Solar spicules, with velocities sometimes exceeding 100 kilometers per second, represent one of the most vigorous mass motions in the chromosphere. Estimates suggest that the total mass flux carried by spicules could surpass that of the solar wind by an order of magnitude, signifying their importance in maintaining the solar atmosphere. The precise role of spicules in energy transfer and coronal heating is a frontier topic in solar physics. The Sun's internal magnetic field likely includes strong toroidal components buried beneath the visible surface, generated and stored in the tachocline. While these deep fields cannot be observed directly, their presence is inferred through surface magnetic phenomena and heliosysmic constraints. Understanding this hidden magnetic reservoir is crucial for models describing the origin and modulation of solar magnetic cycles. Coronal mass ejections, CMEs, exhibit a wide range of masses, typically between 1012 and 1013 kilograms, and energies up to 1025 joules. These enormous expulsions of plasma and magnetic fields can significantly disturb Earth's magnetosphere upon arrival, causing geomagnetic storms and auroral displays. Studying CME initiation and propagation is essential for improving space weather prediction capabilities. The Sun's photospheric magnetic field is characterized by a mixture of polarity regions, with spatial scales ranging from a few hundred kilometers to large active regions spanning tens of thousands of kilometers. The interaction and evolution of these regions produce a constantly changing magnetic topology that governs energy release in the solar atmosphere. Advances in magnetographic instrumentation allow precise tracking of these fields over time. Solar cycle data show that the distribution of sunspots shifts from higher latitudes at the beginning of a cycle to lower latitudes near the end, a phenomenon known as the migration of active latitudes. This migration creates the characteristic butterfly diagram when plotting sunspot latitudes versus time. This pattern reveals important information about the evolution of the solar dynamo and magnetic field emergence. Solar noise storms, continuous radio emissions centered near active regions, often persist for days and are linked to electron acceleration in coronal loops. These noise storms are a significant persistent feature of solar radio emission and contribute to the solar radio background. Understanding their origin provides insights into coronal electron populations and magnetic activity cycles. Magnetic reconnection in the sun's corona can produce superarcade downflows, dark, finger-like features that descend through post-flare loops after a major flare. These downflows are thought to represent retracting magnetic field lines as the magnetic configuration relaxes to a lower energy state. Observing and modeling these structures paints a dynamic picture of post-eruption energy redistribution. The solar atmosphere contains a low-density plasma extending millions of kilometers outward, where the density falls off exponentially with height. This tenuous medium, although sparse, facilitates the propagation of solar energetic particles and shapes the heliosphere boundary. Remote sensing of coronal density profiles through spectroscopy and radio occultation methods informs models of solar wind formation. The sun loses angular momentum through the continuous braking action of the solar wind, a process known as magnetic braking. Charged particles streaming outward are magnetically coupled to the rotating sun, carrying away angular momentum and gradually slowing the sun's rotation over billions of years. This spin-down influences the star's internal dynamics and magnetic cycle evolution. The formation of sunspot groups is linked to the buoyant rise of twisted magnetic flux tubes through the convection zone. These flux tubes emerge at the photosphere as bipolar pairs with characteristic tilt angles influenced by the Coriolis force. Studying the morphology and dynamics of sunspot groups informs theories about flux emergence and solar dynamo action. Solar ultraviolet (UV) continuum emission near the Lyman continuum edge, around 91.2 nm, arises from the recombination of ionized hydrogen in the chromosphere and transition region. This UV radiation plays a key role in ionizing planetary upper atmospheres and drives the photochemistry essential for atmospheric composition and evolution. Variation in these UV emissions correlates closely with solar activity levels. The solar transition region is characterized by sharp gradients in temperature and density, occurring over spatial scales of a few hundred kilometers. This narrow layer acts as a conduit through which energy and mass flow upward from the chromosphere to the corona. High-resolution observations from instruments like IRIS, Interface Region Imaging Spectrograph, provide detailed views of this highly dynamic and structured region. Solar surface brightness is punctuated by facular patterns, bright, irregularly shaped features associated with concentrated magnetic fields often located near the edges of granules or in network regions. Faculae contribute significantly to increases in solar irradiance during periods of high magnetic activity, partially offsetting irradiance reductions caused by sunspots. Their contrast changes with viewing angle, making facular contributions more pronounced near the solar limb. Radio wave observations of the sun reveal distinct burst types, including type II bursts associated with shock waves driven by coronal mass ejections, and type III bursts from electron beams traveling along open magnetic field lines. Each burst type has characteristic frequency drift rates and durations, serving as diagnostics of energetic processes in the corona and solar wind acceleration regions. These radio phenomena are important indicators of eruptive solar events. The sun's atmosphere exhibits complex filamentary structures in extreme ultraviolet and X-ray emissions, often outlining magnetic field lines and revealing intricate plasma morphologies. These filaments trace magnetic loops connecting regions of opposite polarity on the solar surface and can expand thousands of kilometers into the corona. Mapping these features enables reconstruction of the sun's coronal magnetic field topology. Solar flares release energy across all electromagnetic wavelengths, but often produce intense emissions in the hard X-ray and gamma-ray regimes. These high-energy emissions are signatures of accelerated electrons and ions colliding with denser plasma in the lower atmosphere. Understanding particle acceleration mechanisms during flares remains a central challenge in solar physics, with implications for fundamental plasma processes. The photospheric convective pattern includes a hierarchy of structures: granules 1000 km, mesogranules 5000–10,000 km, and supergranules 30,000 km. Each scale represents successively larger convection cells with distinct lifetimes and flow characteristics, collectively governing energy and mass transport near the solar surface. The interplay of these convective scales creates the dynamic environment in which magnetic fields evolve. The Sun's atmosphere contains small-scale jets and intermittent heating events known as nanoflares, which may individually release relatively modest energy, but cumulatively contribute to coronal heating. Detecting and quantifying nanoflares challenge observational capabilities due to their short duration and low intensity. The study of nanoflare occurrence statistics is crucial for confirming their role as coronal energy sources. Solar irradiance in the near-infrared spectrum contributes significantly to the total energy input Earth receives, affecting thermal radiation and atmospheric heating. This infrared component varies slightly with the solar cycle, influencing the energy balance of Earth's climate system. Accurate characterization across the full spectral range is necessary for precise climate modeling and interpretation. The magnetic polarity inversion line, where the Sun's surface magnetic field reverses direction, is a common site for filament formation and flare initiation. The complexity and shear in magnetic fields along these inversion lines provide the free energy required for explosive events. Detailed magnetogram observations allow forecasting of potential solar eruptions by analyzing these regions' magnetic shear and topology. The Sun's differential rotation is accompanied by radial shear layers not only at the tachocline, but also near the surface, where rotation speed decreases with depth within the top few percent of the solar radius. This near-surface shear layer likely plays a role in generating small-scale magnetic fields and modulating surface activity. Heliosysmic measurements provide crucial data characterizing the magnitude and structure of this shear. Solar energetic particle fluxes frequently exhibit anisotropies, with particles detected early during eruptive events arriving preferentially along magnetic field lines connected to the flare site. These anisotropic distributions evolve as particles scatter and diffuse through the heliosphere. Understanding SCP transport and anisotropies inform space weather risk assessments for spacecraft and astronauts. The Sun's coronal loops, arched magnetic flux tubes filled with hot plasma, span hundreds of thousands of kilometers and outline the magnetic field structure of active regions. These loops show a range of temperatures from 1 to several million Kelvin and evolve on timescales from minutes to days. Studying loop dynamics provides insight into energy release, plasma confinement, and magnetic reconnection in the solar atmosphere. The solar neutrino flux is influenced slightly by variations in solar core temperature over the course of the solar cycle, though these changes are subtle and challenging to detect. Long-term neutrino observations may eventually yield constraints on solar core processes and cyclic effects, adding a novel dimension to solar monitoring beyond electromagnetic signals. The phenomenon of solar supergranulation was first identified through Doppler measurements of horizontal flows on the Sun's surface, revealing large convective cells with typical lifetimes of about 24 hours. These supergranules organize magnetic flux into a network at their boundaries, shaping the distribution of small-scale magnetic elements. Supergranulation remains a subject of detailed investigation to understand its origins and influence on magnetic field transport. The solar corona contains trapped populations of highly energetic electrons, producing synchrotron and gyrosynchrotron emissions detectable at radio frequencies. These trapped particles provide diagnostics of coronal magnetic field strength and topology. Observations of these radio emissions, particularly during solar flares, allow reconstruction of particle acceleration and confinement mechanisms. Above the photosphere, the solar atmosphere exhibits rapid changes in density over scale heights of few hundred kilometers, with density decreasing exponentially from about 1017 particles per cubic centimeter at the base to less than 10.8 near the corona. These density gradients affect radiative transfer, wave propagation, and ionization state equilibria. Accurate modeling of density profiles is essential to interpret spectral observations and infer physical conditions. The solar H-alpha spectral line, centered at 656.28 nm, is a critical diagnostic of chromospheric conditions, sensitive to temperature, dynamics, and magnetic activity. H-alpha filters enable imaging of solar prominences, filaments, and flare ribbons with high contrast, making it a mainstay in solar observations, both from ground-based observatories and spacecraft. Changes in H-alpha emission provide immediate evidence of chromospheric heating events. Solar wind streams emanating from coronal holes are typically faster and less dense than those originating near active regions. These high-speed streams can interact with the slower solar wind ahead to form co-rotating interaction regions, CIRS, which are sources of moderate geomagnetic disturbances on Earth. Monitoring coronal hole locations over the solar cycle helps predict the occurrence and impact of these high-speed streams. The Sun's photosphere exhibits a continuum spectrum resulting mainly from H-ion absorption, which dominates opacity in the visible range. This continuum provides the bright solar background against which absorption lines are imprinted. Understanding the opacity sources and continuum formation is fundamental for accurate spectral modeling and element abundance determinations. Solar telescopes equipped with spectropolarimeters measure the polarization of sunlight, enabling the reconstruction of vector magnetic fields on the solar surface. The Zeeman effect, splitting spectral lines in the presence of magnetic fields, allows determination of field strengths and directions. These measurements are key to understanding the complexities of sunspots, active regions, and the processes driving solar magnetism. The modulation of cosmic rays by the solar magnetic field causes an anti-correlation between solar activity and cosmic ray intensity observed near Earth. During solar maximum, stronger magnetic fields and enhanced solar wind reduce the flux of galactic cosmic rays reaching Earth. This modulation influences the production of cosmogenic isotopes in Earth's atmosphere, which serve as long-term records of solar activity. Solar eruptive events often produce shock waves detectable through type II radio bursts and interplanetary shock fronts measured by spacecraft. These shocks accelerate particles and compress magnetic fields, affecting energetic particle populations in space, whether conditions well beyond Earth's orbit. Characterizing shock properties informs models of particle acceleration and heliospheric dynamics. The Sun's radiative equilibrium temperature at the photosphere balances the energy generated in the core with the energy radiated into space, resulting in a relatively stable temperature around 5780 Kelvin. Small deviations from this equilibrium can lead to observable luminosity and radius variations. Understanding this equilibrium serves as a baseline for interpreting solar variability and evolutionary changes. Magnetohydrodynamic (MHD) waves propagating through the solar interior contribute to the redistribution of angular momentum and magnetic fields. MHD wave interactions can affect differential rotation profiles and the solar dynamo's efficiency. Numerical simulations incorporating MHD processes provide crucial insights into the coupling of solar plasma motions and magnetic field evolution. Solar brightness variations on timescales from minutes to decades are influenced by a superposition of convective, magnetic, and rotational phenomena. High-frequency oscillations correspond to P-mode waves, while longer-term changes reflect solar activity cycles. Accurately separating these contributions is essential for understanding solar variability's impact on Earth's climate system. The sun's corona emits a complex centimeter-to-decimeter radio spectrum, originating from thermal bremsstrahlung, gyroresonance, and plasma emission mechanisms. Each emission type traces distinct physical conditions and regions, such as active regions or quiet corona. Radio observations complement optical and ultraviolet solar studies by revealing plasma densities and magnetic fields in otherwise inaccessible layers. The development of sunspot pairs often follows Hale's polarity law, which states that leading and trailing sunspots in bipoles have opposite magnetic polarities depending on the solar hemisphere and cycle phase. This law reflects systematic aspects of the underlying solar dynamo and flux emergence patterns. Violations or exceptions to Hale's law, although rare, provide important clues to magnetic field complexities. Solar irradiance variability measurements increasingly rely on combined satellite observations and ground-based proxies calibrated over decades. These reconstructions extend knowledge of solar output beyond the satellite era, facilitating climate studies that account for natural solar forcing. Improving these datasets remains vital for distinguishing solar influences from anthropogenic factors in climate change research. The sun's photospheric limb displays an enhanced brightness feature known as the bright limb or limb brightening, particularly visible in certain spectral lines, such as the chromospheric Ka-IIK line. This localized brightening results from enhanced emission at oblique angles, influenced by temperature and density gradients. Observing limb brightening offers additional diagnostics of the solar atmospheric structure. Solar flares often show impulsive and gradual phases, with the impulsive phase characterized by rapid particle acceleration and emission spikes in hard X-rays and gamma rays. The subsequent gradual phase involves thermal plasma heating and soft X-ray emission from flare loops. Time-resolved observations of flare phases shed light on energy release and plasma dynamics mechanisms. The solar cycle's amplitude varies significantly from one cycle to another, with some cycles exhibiting unusually high sunspot counts and others markedly lower activity. This variability, challenging to predict precisely, stems from complex and nonlinear dynamo processes. Studying these variations aids in understanding long-term solar behavior and its effects on space and terrestrial environments. The piecewise structure of the solar atmosphere's temperature gradient features the temperature minimum region at the base of the chromosphere, where temperature reaches around 44.0 K before rising sharply through the chromosphere and transition region. This minimum plays a key role in the formation of molecular species and some spectral lines detectable in solar observations. Investigations of this region help elucidate cooling and heating mechanisms governing lower atmospheric layers. The kinetic energy of the solar wind at Earth's orbit averages about 1 keV per particle, with energetic protons and electrons streaming outward from the sun. This outflow represents a steady transfer of mass and energy into interplanetary space, influencing planetary magnetospheres and space weather. Variations in solar wind parameters correlate with solar activity and affect conditions throughout the heliosphere. Solar global oscillations include both pressure, P, modes and gravity, G, modes. While P modes are well observed and analyzed, detection of G modes remains elusive due to their small amplitudes at the surface. Gravity modes hold the key to probing the sun's core conditions more directly, complementing P mode constraints on the outer interior. Continued observational efforts aim to isolate and characterize these elusive modes. Finally, the sun's dominant energy transport within the convective zone occurs by buoyant plasma motions, but magnetic fields can locally suppress convection, giving rise to magnetic features such as sunspots. These dynamic interactions between plasma and magnetic fields modulate solar surface patterns and underpin much of the observed solar variability. Understanding these processes bridges stellar physics, plasma physics, and magnetohydrodynamics in one close-to-home example.